Okay, so we're starting chapter 3 today, and the focus of this chapter is functions. We're going to split this chapter up into two parts, since it's pretty robust. In the first half, we're going to focus on just the basic characteristics of functions. How do we determine if something is a function from an equation, from a table, from a mapping diagram, from a graph? And what are the characteristics that need to be present for something to qualify as a function? So we're going to be focusing on the basic building blocks for functions. And then in the second part of the chapter, we'll hone in on linear functions in particular and what those characteristics need to look like. So first of all, let's define, I know it's review, but let's define functions, right? Well, before we talk about that, let's talk about a relation. Okay, so there's a whole lot of relations out there, and a relation is anything that pairs an input with an output. Okay, so a relation pairs inputs with outputs. When a relation is given as an ordered pair, the x coordinates are always considered to be the input into the relationship, into the relation. And the y coordinates are always considered to be the output. Okay? Now, here's the big distinction. When a relation pairs each input with exactly one, and that is the big definer here, exactly one output. So when a relation pairs each input with exactly one and only one output, that is what we call a function. Okay. I know that sounds like a pretty standard idea. I think one of the things that is the hardest about functions to kind of wrap your brain around is because almost all the equations you already work with are functions. So it's hard to kind of put your brain around it when it's like, well, doesn't everything do that? Well, the answer is actually no. The majority of the equations or relations that are not in this function family, a lot of them you haven't really worked very in depth with yet. And so it gives us the impression, well, isn't everything a function? It isn't. And as you get into Algebra 2, pre-calc, calculus, you're going to get to know more and more families of, equations that don't fit into this category. Okay. The quickest example I can give you of something that is a relation but not a function that you might be comfortable with is square roots. Okay, so if I think about, okay, let's say that I plug in 9 here, and I ask myself, what would be my output, right? This is going to pair my input with an output here, right? But if I go ahead and evaluate this particular equation of the square root of x, the reality is that there are two outputs that make this true. The square root of 9 could be 3, but it could also be -3. Both of those are true and accurate. Okay, the square root of 9 is 3, and it's also -3. And so that gives you a good example of a situation where you have an input-output relationship, but this input is not paired with exactly one and only one output. In fact, it has two outputs, right? So this is an example of a relation. It's an equation. You can graph it, you can plot points, but it's not part of the function family. By definition, a function has to be a situation where every time you plug in an input, there's only one possible correct output for that. Okay, so let's see. We are going to really describe these functions in lots of different ways. We're going to explore several of these. When we're talking about functions and determining if something's a function, we can do that from an equation. We could do it from a set of ordered pairs that we've been given, data points. An input-output table, which is very similar to this, just a different type of organization, where you have it in a table. Written description, the words, written description using words, like being able to take a word problem or a situation and determine if that is a function relationship. Okay, mapping diagrams and graphs. So these are all ways of displaying and communicating this data in different ways. And we'll be able to look at what functions look like in all 6 of those. Okay, so all of these are examples of functions. Okay, if we take a look This is ultimately our big definer here, the fact that each input has exactly one output. So I can look at this equation and think about, well, no matter what I plug in here, if I take any value that I plug in, I multiply it by 2 and I add 3, will I ever really be able to get two different answers that are both correct as an output? And for this one, the answer is no. This is a good example of something that is a function versus something that was not a function. Here I could plug in the 9 and I could get two correct outputs, and they're both equally correct. Where here, no matter what I plug in, you could spend the rest of the evening kind of checking numbers, and as long as you did your math correctly and you multiplied by 2 and added 3, there'd only be one possible output solution for this. So that is a function. In a set of ordered pairs, we're looking to see if I plugged in 0 and according to this my output was 1. What I'm really looking for is to make sure that 0 didn't get plugged in later on again and paired up with a different output. So this is the whole, and you probably remember this from last year, this is the whole concept of make sure that X does not repeat. Make sure X does not repeat with different outputs or different answers. As long as that's the case, you can safely conclude that that is a function. So I've got 0, 1, 1, 12, 2, 18, 4, negative 8, 15, 17. So 0, 1, 2, 4, 15. My X values never repeated, and more importantly, they never repeated with different answers or different outputs. So this is a function. Same thing here in this input-output table. I see that my X values do not repeat. They're never paired up, the same X with two different answers or two different outputs. So that's a function. Okay. This one, the word situation, the temperature outside was 82 degrees Fahrenheit at 10 a.m. and it rose 2 degrees an hour for the next 6 hours. So if it is increasing 2 degrees every time, it's not going to be possible for it to have the same temperature twice for that same hour. Or sorry, two different temperatures for that same hour. So that is a good example of a function. In a mapping diagram, we're looking to make sure that each X input has only one arrow pointing to a single unique output. So there's the whole exactly 1. So if, according to them, if the input was 1, the output was D. Notice it doesn't even have to be numbers necessarily because the concept is bigger than that. The concept here is simply that for an X input of 1, there's only this possible output. For an X input of 2, there's only a C possible output. For an X input of 3, there's only a C output. And this brings up a good point. The Y values can repeat. It is okay if when I plugged in a 2, C is my output. And then when I plugged in a 3, C is my output again. That's okay. What is not okay is if I had plugged in a 2 and gotten B and C as outputs, gotten multiple outputs for that input. That would be the deal breaker. So multiple arrows coming out of the X is kind of your giveaway here that that would not be a function. But as long as I have one arrow going out of the 2 and pairing it with the output C, it's okay if this 3 also has the arrow pointing toward the same output. It is okay for these guys to have the same output as long as they only have a single output. And then on graphs, same thing. If we look at this X value at 0, 8 is the only output. At 1, 6 is the only output. At 2, 4 is the only output. 3, 2 is the only one, and so forth. So we'll talk a little bit about a graph test that we can do quickly to determine, if you recall, but this is definitely a function. So these are all examples of functional relationships here, okay? So if we were going to do A here, explain why the graph shown above represents a function, we could say something like, well, because each X coordinate has only one Y coordinate output. Only one. That's the key. Okay, that's the big idea right there. Okay, and in part B, it says describe the function represented by the above graph using words as an input-output table and as a set of ordered pairs. Okay, so we're still working with the graph. We want to be able to sort of translate that same information or data and describe it using words, using an input-output table, and using a set of ordered pairs. Okay, so let's start with let's start with using the words. So if I look at my points here, and I need to describe this pattern or what is happening here, it looks like we started at 8, and as x increases by 1, y seems to decrease by 2 every time. Okay, so I might say something like as simple as that, as x increases by 1, y decreases by 2. Okay, if I want to take that same information or data and describe it in an input-output table, it would essentially be just a reorganization of the same information. I have an ordered pair at 0, where x is 0, and y, the corresponding y output was 8. Okay. When my input was 1, the corresponding y output was 6. When x is 2, my corresponding y output was 4. When x was 3, my corresponding y output is 2. And when x was 4, my corresponding y output was down here at 0. And so that describes the same information or data in an input-output table. And then the last one is set of ordered pairs. It's actually going to be very similar to this, but instead of the table format, we're going to essentially list the ordered pairs. So the first ordered pair in this set of numbers was the ordered pair 0, 8. The next ordered pair was 1, 6. The next one was at 2, 4. Then 3, 2. And last but not least, 4, 0, and that ends the set. Okay, so that would be the same information sort of described verbally as a set of input-output table and a set of ordered pairs there. Okay. All right, what about C? It says, explain why the following input-output table and mapping diagram are examples of relations and are not functions. Okay. So what we're looking for here is some evidence or example where x would be paired up with more than one output. So if I look across, the easiest way to do this on a input-output table is look to see if x repeats at any point, and then see if it does repeat if it has different outputs. So when I look across my x coordinates here, my inputs, I notice right away I have a 1, a 4, 1, 8, 2, 1, 6. So here's my 1 being repeated. And if I look to see what the output was for that input, they're different outputs. So this is my deal breaker, is what I like to call it, to be a function. This is why this can't be a function. Because according to this, the same x input, in this case 1, right, has two different outputs, y outputs. Okay, so when they plugged in an x of 1, they got an output of 5, and then later on when they plugged in the same x of 1, they got an output of 2. So same x input paired up with two different y outputs. That's a relation, all right, but it is not part of the function family because it does not meet that criteria. For our mapping diagram, it's similar to what we talked about up there. We have an input of 1 is paired up with an output of D, and then an input of 2 is paired up with both B and C. Okay, so right in here is where the evidence is that we have a relation that is not a function, right there. And the reason is that the x input the x input of 2, in this case, maps to two different outputs. Okay, that means that essentially is synonymous with what was going on here, in the sense that you're looking at an x input of 2 that has two different possible outputs. So our output is not unique. Okay. All right. So just jogging your memory here. I know this is review, but I want to make sure that we're feeling really comfortable with the basics of what makes something a function and how to tell from different situations. Okay. So look at this A and B. There you go. Make a mapping diagram to determine whether each relation represents a function. So we're reviewing two things. We're reviewing how to make a mapping diagram, and as well as how to determine if something is a function. Okay, so one of the key differences between a mapping diagram and a set of ordered pairs or a graph and so forth is that we typically don't write repeating values, because we're using the arrows to indicate that. So what that means is, when I go to make my mapping diagram, first of all, we always have two bubbles or two boxes. One represents your inputs, that's usually on the left. Okay, and in this case I have inputs, so I'm going to make my little bubble here. And I have inputs of 0, 1, 2, 3, and 4. Those are all different, so I'm going to list them all. 1, 2, 3, 4. Okay, so 0, 1, 2, 3, 4. And then I have a second bubble on the right side that has the possible outputs. And in this case, 8 is the only output. I'm not going to write 8 5 times. That's one of the big differences of mapping diagrams, is that we only write it once. The arrows are going to indicate to us if things repeat. So in a set of ordered pairs or a table, we would repeat it as many times as needed, but in a mapping diagram, we don't do that. Okay. So let's see. Now we use our arrows. So when the x was when the x input was 0, our output was 8. So I'm going to draw an arrow point mapping that. This x input of 0 maps to an output of 8. There it is. Okay. And then we'll do the next one. An x input of 1 maps to an 8. Also, well, yeah, because that's the only output we had. Right? X input of 2 maps to 8, and you get the idea here. 3 also maps to 8, and 4 maps to 8. So this might be tempting to be like, well, that can't be a function. Actually, this is a function, because the x's didn't repeat. Remember, we talked about that earlier. These guys can repeat all day, not a big deal. As long as every time I plug in 0, this is the only possible output, we are okay. So as long as only one arrow is shooting out of each one of these, then we know that this is a function. So yes, this is a function. Now compare that to what happens in option B here. Okay, we're gonna still make a mapping diagram. We start with our input bubble here that has the list of any input values. And when I look at the inputs, it's the same input all the way across. So again, we're not gonna repeat that. We'll write it once. We're gonna use arrows to show any repetition or any mapping. So I only need 1, 8. That's really important. And then for my outputs, the Y outputs, I've got 0, 1, 2, 3, 4. So very similar example, but you can see there here the contrast, the differences. So I've got an output of 0, 1, 2, 3, and 4. Okay, and when I map, basically this is telling me, hey, we plugged in a value of 8 for x, and we got a y output of 0. So we map that. And then they're saying, oh, by the way, we plugged in an 8 again, and we got an output of 1. Oh, goodness. Okay, so the same input is giving me 2 outputs. And then we do the next one. You know, when we plugged in an 8, we got a 2 out. So now we've got 0, 1, 2. All the same input is giving me multiple outputs here. And you can see the same thing's going to happen here. 8 is going to map to the 3, and 8 is going to map to the 4. Now, this is an exaggerated example, but the important part is to see, yes, if you have an input with more than one arrow coming out of that same number, meaning that input is mapping to multiple outputs, that is not a function. Nope, this is not a function. Okay, so let's test that. Let's see how that looks. So determine whether each relation represents a function or just a relation. Explain your reasoning, okay? So if I look at a mapping diagram, remember what we're looking for. We're looking for situations where an input might have more than one output. Well, 1 mapped to 8 and only 8, so that's okay. 2 mapped to 9 and only 9, we're still okay. 3 mapped to 10 and it mapped to 11, this is my deal breaker. Ding, 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 right? This should sound an alarm off and say, oh, wait a minute, same input, 2 outputs. Our outputs are not unique here. This X input does not have only one output, it has more than one. This is not a function. Okay? In a graph, we're looking for the same concept, and we're going to elaborate a little bit on this in a moment, but if you remember a little something called the vertical line test, then you're in good shape here, right? So we're testing essentially the same concept or idea here, that for this X value, there's only one output, and there is. So when X is 0, the only option here was 8, so we're good. When X is 1, the only option here was 6, and nothing else, so we're still all right. Okay, when X is 2, 4 is the only option, so we're good. And then you can see the same thing here and here and here, but then look here. When we get to X equals 5, it looks like X equals 5 has a Y coordinate at 4 and also at 5. So you have 2 Y coordinates for the same X input. That is not a function. Okay, so right in here, it fails what we tend to call that vertical line test, which again, we'll elaborate a little bit more. Okay, but it fails it there, and in fact, it fails it again a little bit later. This one's okay, but then right in here, you see it happen again. When X is 7, there's 2 possible outputs for that input. That's your deal breaker. So whether it's the first one, I guess I'll finish this one off. Whether it's that first one or this one, these both are examples or evidence for why this is not a function. Okay. Now, from a set of ordered pairs, we did a couple like this. We really are just looking to see, this will repeat when we're doing a set of values or a table, right? Things do tend to repeat. So we're looking for the same thing we would on that table up there. We're looking to see that the X value doesn't repeat with different outputs. So if I look at my X's, I've got -2, -1, 0, 1, and 2. None of those X's ever repeated, so we are okay. With the evidence we have, we can conclude that this is a function. Okay? We're going to test again on this one. So we've got a -2, a -1, a -1 again, ding, ding, ding. This is where I need to check things. And then 0, 1, 2. So those are okay. But here I have the same X coordinate input, and it is being paired with different outputs. So this right here is a reason why this is not a function. Okay? So just reviewing what this looks like from a graph, from a set of ordered pairs, from a mapping diagram, from a table of values, so forth. Okay? How about these examples? Each radio frequency, X, in a listening area has exactly one radio station. So each radio frequency has exactly one radio station. Well, here are the key words, exactly one. Each X has exactly one Y. Okay, so even if you kind of omitted the other, each X value here has exactly one Y, that is definitely a function. In fact, that is the very definition. So yes, this guy is a function. Okay. How about H? X equals 2. Well, I'm going to give you a hint. It's been a while since you guys have messed around with this, but I'm going to remind you that when you see something like X equals 2, when we're dealing with equations and graphs, this is actually the equation of a vertical line. Okay, so if you think about a vertical line, and we graph that, just to get an idea of what that might look like, it'd be here where X equals 2. This is the graph of that. It's basically just a solid line up and down. And so does that pass that vertical line test that we hinted about? Does it have one unique point output for each input? Absolutely not. In fact, Here x is 2, and all of these are outputs that are possible. So this is definitely not a function. In fact, vertical lines are never a function. In fact, that's why we call it the vertical line test. So not a function here. Okay. However, this kind of line is that y equals mx plus b line, y equals 2x plus 3. We have a slope of 2, a y-intercept. We're probably looking at a straight line that has a slope of 2 that looks somewhat like this. Or you could just test some points in and try to think of ways that this could possibly have 2 right answers, but it won't. This is definitely a function. Okay. Let's take a look at J. X is equal to y squared with inputs 4 and 9. So they give you some specific ones to test, and you can base your decision on those inputs. So the question is here, if I plug in a 4 for x, right? If I plug in a 4 for x here, and I solve this to find out what this output would be, we'll find out if there's more than one possibility here. Well, to find out what y is, what we're really asking is what number squared gives us 4. Okay, well, we know that 2 squared gives us 4, but hold up, we also know that negative 2 squared gives us 4 also. So for this value of 4, we have 2 different y outputs. They both work, okay? And that means this is not a function because there's an ordered pair here at 4, 2, and there would be an ordered pair here at 4, negative 2 also. So that's enough information for us to say, hey, you know what? This is not a function. Okay? How about this one? If x is equal to the absolute value of y, reminder, absolute value is the distance from 0. It makes whatever's inside always positive. So if we plug in an x1 here, we ask ourselves, what numbers have an absolute value of 1? What number is 1 unit away from 0? Well, 1 is definitely an option here. So we have an ordered pair at 1, 1. And is that the only one? Well, actually, no. Negative 1 also has a distance of 1 unit. So x could be 1 and have an output of negative 1. So this guy is also not a function. Okay? All right. Let's try a few more. If you want at this point, you can pause the video. You can try these 3 on your own and then press play again and check your answers and see how well you did. So maybe try to work these 3 independently and then press play and follow along and decide if you think that these are functions or not. So you press pause now, work them out. And if you press play again, hopefully, you're going to notice here this is not a function. So check that one. Okay, you have the same input with 2 different outputs. For number 2, it is a function. X does not repeat. And for number 3, the same television station X can be found on more than one channel. So X has more than one Y, not a function. Okay, so hopefully you did okay on those on your own. If not, definitely ask me some questions when we get to class or come in the morning or at go time. Let's finish off with the vertical line test. It's a concept that you should be familiar, and I've actually hinted about it a couple of times throughout these notes, but let's formally talk about it. From a graph, this is our go-to test when we are trying to determine if something is a function from a graph. So a graph represents a function when no vertical line passes through more than one point on the graph. Okay, so if it looks like this, right? They gave an example, but the point is you can grab your pencil and test because this should be everywhere on that graph. Anywhere on this graph, I should be able to lay a straight vertical line and only intersect one point at any given time. There shouldn't be any points directly above one another. That's what would fail the vertical line test. So this is a great example of a function here. every time I kind of line up my pencil with any x coordinate, I only have one y coordinate or y output or one point along that path. But then here is a good example of something that is not a function. There's like this one spot right here where I might have only 1 point or no points, but as soon as I get past that, pretty much no matter where I put my pen or pencil or ruler, it's striking this graph twice, right? It's hitting this graph in more than one location, here and here, for example, which means that this x coordinate has two different y outputs. Okay, and that makes that be not a function. So let's use a vertical line test to make some quick decisions here about whether graphs are functions or not. Okay, so if I look at number 4 and I'm using my pencil here, I've got, okay, 1 point here, that's okay, 1 point there. But then right in here, right, I see that in this vertical line location, I would have 2 points intersecting or touching this vertical line. That means I have two y outputs for this same x input. So right in here, look at me using straight stuff around here I have laying around. You don't need a ruler. You can use any straight edge. There it is. Okay. So right in here is my deal breaker. This is not a function because of that spot right here where that x value has more than one output. So this is not a function. It does not pass the vertical line test. Okay. Look at number 5. If we kind of go through with our pen, pencil, straight edge, there isn't anywhere here where my curve or my graph touches my pencil more than once. No matter where I put it, any x value, when I go up, there's only one location on this graph for that x value, so this is a function. This passes the vertical line test. Okay. Let's take a look at number 6. It's a little hard to see. We might need to emphasize the points that they have for us are here, 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 and there. And make it easier to see. Again, we can go through, and at this x value, there's one output only. At this x value, there's one output only. At this x value, one output. At this x value, one output. This definitely passes the vertical line test, so it is a function. And last but not least, this guy right here, you know, it's pretty much anywhere I put it here, starting where the graph is, it is definitely, you know, intersecting or touching this graph in two different locations. So for pretty much all of these x values, there are two y outputs, right? One right above the other. That means it fails a vertical line test, and this is not a function. It's a very similar example to the one they had up at the top. Okay, so hopefully now I've jogged your memory on how to determine if something is a function from graphs, from a situation, from a set of ordered pairs, from an input-output table, from mapping diagrams, all of these different representations of your data. Hopefully you can look at it and know what to look for and to decide, is it or is it not a function.